This tutorial describes the process of solvent extraction as it is used in the analysis of several different radionuclides. When this module is completed, you should be able to list the 5 steps involved in a typical solvent extraction protocol. Define the term hydration layer. Explain how complexation ligands promote the migration of ions into nonpolar solvents. You should be able to calculate the volumes or the number of re-extractions required to extract a given fraction of a radionuclide based on its distribution ratio. You should be able to discuss the similarities and differences between traditional solvent extraction and solid-phase solvent extraction. The key concepts identified in this tutorial are: solvent extraction involves many different basic chemical principles. The charge density of a radionuclide and its hydration sphere will be lowered when ligands are used that can complex with the radionuclide being determined. The lowering of the charge density allows for extraction into nonpolar solvents. And the separation of the radionuclide of interest and contaminants, both radioactive and stable, can be achieved by selective chemical conditions creating differences in solubility. Solvent extraction is a process whereby 2 immiscible liquids are vigorously shaken in an attempt to disperse one in the other so that solutes can migrate from one solvent to the other. The picture on the right shows the shape of a traditional separatory funnel. When the 2 liquids are not shaken, the solvent-to-solvent interface area is limited to the geometric area of the circle separating the 2 solvents. However, as the 2 liquids are vigorously shaken, the solvents become intimately dispersed in each other. The dispersal is in the form of droplets. The more vigorous the shaking, the smaller the droplets will be. The smaller the droplets are, the more surface area there is between the 2 solvents. The more surface area between the 2 solvents, the smaller the linear distance will be that the molecules will have to travel to reach the other solvent and migrate into it. The shorter the linear distance traveled by the molecules, the more rapid will be the extraction. Why do the molecules migrate from one phase into another? The fundamental reason is solubility. The molecules will preferentially migrate to the solvent where they have the greatest solubility. If the molecules are very polar, they will generally favor the aqueous phase. If the molecules are nonpolar, they will favor the organic phase. The key concept to take away at this point is that the process of solvent extraction requires that the chemist adjust the solution conditions so that the radionuclide of interest is in the proper oxidation state, so that the solution pH is adjusted appropriately for the extraction, that the appropriate complexing agent will form the appropriate complex with the radionuclide of interest, and that a neutral complex that will easily migrate into the organic phase based on those chemical conditions is formed. There are 5 general steps that are involved in the solvent extraction process. They rely on the fact that the solution conditions have been optimized to maximize the extraction for one radionuclide over the others. The first step is to ensure that the proper complexing agents have been added to the aqueous phase so that the extractable complex is of sufficiently low charge density so that the transfer of the radionuclide to the organic phase will be maximized. In the second step, the equilibration process occurs by shaking one of the separatory funnel. Unless otherwise specifically noted in a particular method, the amount of time that the 2 phases are shaken during this step is about 2 minutes. The initial organic phase is separated and set aside. Step 3 involves a process known as re-extraction. The original aqueous phase is extracted with a fresh aliquant of the organic phase of the same volume as the first. This improves the efficiency of extraction of the radionuclide of interest. After step 2 is repeated, the 2 organic phases are combined. The aqueous phases are discarded at this point unless They are needed for analysis of radionuclides not extracted. In step 4, the combined organic phases are equilibrated with a solution of aqueous phase that is of the same composition as the original sample solution, but without any sample. This step helps to ensure that any interfering materials that may have been extracted are redistributed back to the aqueous phase, while the radionuclide of interest remains in the organic phase. This phase is known as the wash and is then discarded. The final step is to strip the radionuclide of interest back into an aqueous phase using a pH and a lower concentration of complexing agent so that migration back to the aqueous phase is favorable. Any ion in an aqueous solution is solvated by water molecules that form a sphere around the ion. Note that in the picture to the right, that the oxygen atoms of the water molecules are facing the central metal ion. Since the charge on the overall ion plus its hydration sphere is still the same as the charge on the metal ion, the charge density, or the charge per unit volume, is reduced. The migration of the radionuclide into the organic phase occurs after the complexation process has occurred. The ligands that replace the primary hydration sphere further reduce the ion charge density, allowing the solvation sphere to be changed from water to the solvent at the interface of the two phases. The diagram on the right is of two different organic molecules that are used as extracting agents for different radionuclides. In each case, the ligand has an ionic counterion charge and a nonpolar aspect to its structure that aids in the overall reduction of charge. Chelating agents all have the property of being able to share electrons with vacant atomic orbitals of a central metal ion. These chelating agents act like a Lewis base, which is any material that has at least one unshared pair of electrons. Chelating agents will therefore usually contain heteroatoms, that is, atoms of oxygen, nitrogen, sulfur, or halogens. Listed on the slide are some of the chelating agents that are used in specific analytical methods for radionuclides. Tri-N-octyl phosphine oxide, also called topo, contains a strong dipole moment centered on the phosphorus-oxygen bond. The oxygen, being more electronegative, is the end that will provide the unshared pair of electrons for bonding with the vacant orbitals of a metal ion. The long side chains of this molecule help to increase the size of the complex metal ion, thus decreasing the charge density and making it appear closer to zero charge. This hydrophobic end also aids in the dissolution in organic solvents. Topo is used in the extraction of uranium, as shown in this module on slide 16. The table on this slide identifies various organic solvents based on their elemental characteristics. Some solvents are also chelating agents as noted on the chart. The phosphate-based compounds topo and tributyl phosphate, TBP, are liquids at room temperature and can both be solvents and complexing agents, while the sulfur-based compounds, phenylyl trifluoroacetyl-acetone, TTA, and diphenylthiocarbazone, dithazone, are solids, and 2,3-dimercaptopropanol, also called British anti-Lewisite, BAL, is an oily liquid. These sulfur-based compounds are only used in combination with solvents. Most methods that use solvent extraction have used a trial and error approach. The exact nature of the complexes formed and the conditions for their formation and extraction are not nearly as important as the fact that certain combinations of solvents and chelating agents provide the largest differences in the extractability of one radionuclide over another. This slide represents pictorially what we have described as the 5-step solvent extraction process. The key to a successful extraction is that the analyte and the interferent have extractability factors that are at least a factor of 100 different. Keep in mind that the interferent may be a radionuclide or other material, something non-radioactive, that hinders the analysis of the radionuclide of interest. The extractability of a radionuclide is defined by a factor called the distribution ratio, d sub r. The key concept for the overall separation of a radionuclide from any interference is that their solubilities in the two phases should be sufficiently different to effect a separation in a reasonable volume and an initial plus re-extraction process. This means that their d sub r values will be significantly different by a factor of about 100. The equation shown on the right defines the distribution ratio. It is easy to remember because most of the solvents we use are less dense than water, and so they float on top. The equation that the ratio shows is defined by the concentration in both phases after one equilibration. The distribution ratio is simply a mass transfer effect that has been empirically determined. Values of d sub r can range from less than 1 to greater than 10,000. During an initial extraction, we would want to use solution conditions that favor a d sub r for the radionuclide of interest of at least 100. This would mean that greater than 99% of the radionuclide would end up in the organic phase. Performing a second extraction with fresh organic phase on the sample solution and then combining the two organic phases would provide greater than 99.99% removal of the radionuclide of interest from the aqueous phase. How does one select the correct volume to perform an extraction? If we select an amount to remain in the aqueous phase that we deem acceptable, let's say 0.01%, we can determine the combination of number of extractions needed and organic phase volume to effect this using the equation on the right. In this equation, X represents the mass of analyte initially present in the aqueous phase. X sub n represents the mass of analyte remaining in the aqueous phase after n extractions. This equation applies when the volume of organic extractant, V sub organic, is the same each time a successive extraction of the original solution is performed. You will find that one of the results of using this equation is that you can maximize the amount of radionuclide extracted by performing multiple extractions with small volumes rather than performing one extraction with a single larger organic volume. Using the equation from the previous slide, calculate N, the number of extractions required to achieve an extraction of uranium into the heptane phase equivalent to 99%. Hint: remember to convert percentage to a fraction. The solution to problems like these frequently results in an answer that is a number plus a fraction. However, we can't perform a fraction of an extraction. Thus, in order to achieve at least the desired percent extraction, you need to take the answer obtained and round to the next highest integer. Once we have the radionuclide of interest in the combined organic phases, we want to ensure that we have removed as much of the interfering materials as possible. The next step is referred to as washing because we equilibrate the organic phase with an aqueous phase that is isotonic to the original sample aqueous phase, except there are no radionuclides or other interference present. This washing phase helps to eliminate any of the interfering species from the organic phase. Following the washing phase is the stripping phase. This phase involves equilibrating the organic phase containing the radionuclide of interest with an aqueous phase that will break up the organic phase complex so that the radionuclide will redistribute back to the aqueous phase. Usually, the aqueous phase has a significantly different pH than the original extracting solution, and it has none of the complexing agent. Stripping is generally performed as one step, and it usually ensures an overall reduction in volume. A general outline of the EPA method for uranium separation is identified on this slide. As you can see, this not only involves solvent extraction, but co-precipitation and complexation. In the original method, gas proportional counting was used and only total uranium could be reported. However, alpha spectrometry does allow the user to speciate the uranium isotopes and quantitate them separately. The technique of solvent extraction has been used for a long time, and it is very effective at separating radionuclides from interfering ions. The process is based on the formation of a low charge density or neutral complex that will have a higher solubility in the organic solvent than it does in water. When the two solvents are adequately mixed, the complexed ion will migrate to the phase where it has the higher solubility. The empirical function that identifies the extent of this migration is called the distribution ratio. The drawbacks to solvent extraction are that it is a labor-intensive process, and it generates organic solvents as wastes that are usually hazardous waste. In the next slides, we will discuss a new technique that avoids the use of organic solvents by coating a neutral resin bead with a thin film of an organic compound that is not hazardous. This technique is known as stationary phase solvent extraction. This process is one by which an organic chelating agent is sorbed onto the surfaces of an inert ion exchange resin bead as a very thin film. The organic compound is a high boiling point liquid, or potentially a solid material that has an extremely low solubility in water or in acid solutions. The application of the organic compound as a thin film throughout the resin bead allows a tremendous increase in the surface area contact between the aqueous phase and the organic phase. It is far more effective than trying to force two immiscible liquids into tiny droplets by mechanical shaking. The compound used for this process are better suited to complexing with the actinides based on the geometry of the f orbitals of the transuranics. This means that separation from non-radioactive ions is facilitated at the same time as separating out the radionuclides of interest by differential solubility in the organic phase. So by passing an aqueous phase over an SPSE column, a stationary phase solvent extraction column, you have a continuous solvent extraction process. The organic molecules used for SPSE usually have a significant viscosity. In order to uniformly coat the resin bead and all the internal channels, a solvent of lower density and viscosity is used to dissolve the organic material and then equilibrate the resin with that solution. After draining off the solvent, the resin is flushed with water, in which the organic material has basically zero solubility. Since the process of SPSE is different from traditional solvent extraction, a different type of constant associated with a particular organic compound called the capacity factor, or K prime value, is used. Just like in solvent extraction or ion exchange, the larger the value of the capacity factor, the better will be the migration of the ion into the organic phase. Additionally, the bigger the difference in capacity factor for two ions, the better will be their separation on an SPSE column. Thus, as the liquid eluent flows through the column, different ions will be eluted based on the solvent volume and their individual K prime factor with the concentration of the eluent. The process lends itself to batch analysis of samples since the columns can be set up and eluted simultaneously. One of the first SPSE products that were manufactured was UTIVA, where TIVA is an acronym for tetravalent actinide. This particular organic material, diamyl amyl phosphonate, has a particularly strong affinity or capacity factor for tetravalent actinides. The only exception is that uranium-6 is also strongly retained by this column. The two graphs on the right show the capacity factor of this resin as a function of nitric acid or hydrochloric acid concentration. These factors are empirically determined. The americium, as a +3 ion, is not appreciably retained on this resin and effectively washes through, while thorium and uranium-6 are strongly retained. Note that for nitric acid solutions that uranium-6 and thorium are virtually identical in capacity factor. However, if we switch the aqueous phase to 3 molar hydrochloric acid, the separation of capacity factors is about a factor of 100. This difference in capacity factor allows effective separation of these two radionuclides. The extractant molecule shown here, cetylphenyl NN diisobutyl carbamoyl phosphine oxide, or CMPO, is of general value in allowing separation of different transuranic ions from each other. Here again, the graph shows the change in capacity factor as a function of nitric acid concentration for 4 different ions. Note that the values for iron and calcium are generally much lower than for that of uranium and plutonium. Thus, for water samples containing iron and calcium at ppm concentrations, they will easily pass through the resin column at a concentration of about 0.5 molar nitric acid, while any plutonium or uranium will be exchanged. The plutonium and uranium may then be eluted by dropping the acid concentration to approximately 100th molar. For all of these curves of K' versus LU in concentration, it is important to see that the oxidation state of each ion is clearly identified. This is important as the K' value will be different for different oxidation states for each of these ions. The effect that high or low acid concentrations have on capacity factors can also be modified by the addition of other complexing agents. In this example, the concentration of hydrochloric acid is held constant at 1 molar, while the concentration of oxalic acid is increased. The K' value for neptunium-4 falls off much more sharply than does that of uranium-6. Thus, at concentration of 100th molar oxalic acid, effective separation of uranium from neptunium can be achieved. Here again, the oxidation state of the transuranic is important. The table here shows the advantages of both types of chemical separations. It is important to note that these are generalizations, and in specific instances you may have different types of advantages. One of the most significant disadvantages of SPSE for drinking water analysis is that these materials are not part of any EPA-approved method. Therefore, they cannot be used for drinking water analysis under 40 CFR. However, this will be changing in the near future. This concludes our module on solvent extraction. You should be able to describe the 5 steps in the solvent extraction process and the reason for each step. You should be able to calculate how many extraction steps will be needed to remove a given fraction of radionuclide from an aqueous phase. You should be able to describe the importance of mechanical agitation in the solvent extraction process. And you should be able to describe the similarities between solvent extraction and stationary phase solvent extraction.